So in this video we'll look at the preparation of ethene and some of the reactions of the alkenes. So starting off, to prepare ethene, and this you can look at this experiment after this video as well, but in terms of what happens in this experiment, essentially what you have is an alcohol here which is known as ethanol. So what that looks like is a carbon bonded to 3 hydrogens, like so. So there's that CH3 at the end, and then you have another carbon, and off that carbon you have a bond to an oxygen, and that oxygen in turn is bonded to a hydrogen. And then if you look at this carbon right here, it only has 2 bonds. So we'll have to add in another 2 hydrogens to give it there the octet. And if you look at that chemical formula right there, that's C2H5. So there's the 2 carbons, the H5 will be 1, 2, 3, 4, 5, and then the OH is right at the end there, the hydroxyl group. So essentially what we do is we go from this molecule to C2H4. So C2H4 is just carbon. You could put the hydrogens, 2 hydrogens, and that went a bit off there, but 2 hydrogens on both carbons, and then you'll find that both carbons are short 1 bond, if you like, and then you create that double bond right there, and you have yourself C2H4. So if you look at the difference between what changes between this side on the left, this side, until you go over here, like you look at, well, number 1, a double bond is over here and there's no double bond initially. If you look at what actual atoms have been removed, you look at there's 2 hydrogens off this first carbon where there was 3 here, so we may say that one of those hydrogens will be removed. And then also if you look at the second carbon here, we've not alone, there's 2 hydrogens on it, but we've lost all of this. We've lost all of the OH here. And if you take those 2 in green away, you'll be left with C2H4. And then if you do that, you see there'll be a bond free here and a bond free here. That's where the double bond, a bond free from the a bond free from this hydrogen when it's gone, and a bond free from this oxygen, and the hydrogen goes as well, and you see you'll have a bond created then, so that over here if you like, and that allows the octet to be reached. And you need to remember as well, obviously, that in this type of reaction, like if you have a hydrogen atom, and think about what that has, and then you have an OH hydroxyl group, what's HOH, and that is of course water. So water is formed, this is known as a dehydration reaction. So essentially this ethanol, remember eth is 2 carbons, this ethanol is dehydrated because it loses water. Dehydrated to lose water, and you know that from everyday life as well. People say they're dehydrated, they've lost water, and that's essentially what this reaction is. Now and that's the name for the reaction. It's a dehydration reaction, and you also could say that it is an elimination reaction. And now what an elimination reaction is, and we'll look at it again later indeed next year. H2O is a small molecule. It's removed from a larger molecule, this ethanol, to leave behind a double bond in the large molecule, and that's over here. So that's what's known as an elimination reaction. You eliminate a small molecule from a large molecule, leaving a double bond in the larger molecule, or at least that's how we define it at Leavenscert. There's in here you have some glass wool. It needs to be glass wool and not cotton wool, because look at, we're heating it with a Bunsen burner right here. And that's in here. It's just glass wool soaked in a little bit of ethanol. There's aluminium oxide, Al2O3. That's Al3 3 plus and then O2 minus, and 3 of those and 2 of those gives your overall charge there of 0, or oxidation state of 0. And if you, this little solid here just needs to be heated. So the aluminium oxide is heated with a Bunsen burner, a horizontal test tube, and then you collect the ethene, and that's how you prepare ethene. Now, ethene is used in industry. It's used to ripen fruit, so it's a useful gas. If you take fruit from a different country and you from a warmer country or whatever conditions you take it from, and then you can bring the fruit effectively green, so it transports without getting bruised, and then when it arrives you could spray it with ethene and cause it to ripen. So that's what it can be used for. The standard test in alkene can be carried out. So there's a couple of tests. It's a colourless gas with a sweetish odour. Obviously we're not in practical now, so we can't determine that, but you would, if you were there, you would know that. Combustion, ethene burns with a slightly luminous flame. Luminous is that yellow tinged flame, and there's not very much soot. So the soot is present, caused by the presence of large amounts of unburned carbon, effectively. And then the test for CO2 in lime water, you might remember that from junior cert. Carbon dioxide is tested a lot in junior cert. If you bubble it through lime water, the lime water is actually calcium hydroxide, and if you pass the lime water, or we've talked about this before as well actually, but if you pass carbon dioxide through it, you get solid calcium carbonate, and that's actually insoluble, so that's why it turns cloudy. So it's a calcium carbonate, limestone effectively, or lime scale floating in the water, allows it to become that cloudy appearance. And there you have C2H4 and oxygen. This is just the combustion of ethene, and there you have carbon dioxide and H2O. So to test for this carbon dioxide, you would bubble it through calcium hydroxide, otherwise known as lime water, and you get a cloudy appearance. We'll look at that again in water chemistry in more detail, but that's effectively what happens, that reaction. And then water you can test with white copper sulfate, it'll turn blue, or indeed cobalt chloride will turn pink, but a lot of the time that now chemical is no longer used in the laboratory at leaving cell level. The bromination, to brominate something, is effectively to add bromine. So if you, that's a nice test for the presence of ethene. If you add bromine, add it to bromine water is sort of an orange tinge to it, and it will decolorize, and that's how you say it in chemistry, it'll decolorize. Now what exactly happens there is quite simply, I'll give you the brief version, and then next year you'll look at the more complicated version. Effectively, that's CH or C2 is C2, so that's ethene, so there's hydrogen up both of them. Now I'll give you the very brief version of this. You don't have to necessarily worry too much about this for now, but that's bromine there, Br2, so that's like a molecule on its own here. And if you think about this area here where there's a double bond, that double bond area, there's quite a lot of electrons in a small area. There's 4 electrons there, and even that's not perfectly correct, but there's a high density of electrons there. And this thing here, that when you add ethene to bromine water, you can imagine the two of them come in contact, and you know that from rates of reactions. And when that bounces off this double bond here, what actually happens is the electrons in this molecule, even though it's non-polar because it's bromine sharing with bromine, are pushed in that direction. And what that gives rise to is a Br. Because it gets so close, now if you think about it, if the electrons are pushed in that direction, that would leave this end slightly positive, and it would leave this end slightly negative. Now you think about that. Why that is the case? I mean, if the electrons are negatively charged and they're pushed in this direction, well, that's... So it's induced polar. Why are they being pushed away? Because these are electrons here. And when that happens, it can happen with such a direction, if you like, that this becomes more and more positive to the point where it breaks off as Br plus. And now it will attack. Remember we talked about the bonds yesterday in a double bond. The first bond that is created between two carbons is all happy because there's one carbon there, there's another carbon, the nucleus of both of them. And then the second bond that forms, remember, is above. So they don't head-on overlap or sigma. The second bond, or the second bond in a double bond, is always a pi bond, a weaker bond. Why is it weaker? Quite simply, the electrons are not directly between the two nuclei. They lie above the plane if the nuclei are one. So the first one's right in the middle, that's a stronger bond. The pi bond is still strong, but it's weaker than sigma. And the bromine, this Br plus, when two carbons have a pi bond like this in this double bond, that Br plus will break that bond. I'm really talking about this one in here, but just to over dramatize it. And you get then a Br attached. Now I'm going to skip over maybe the complete ins and outs, just to give you an idea if these things all make sense. You know, all this chemistry makes sense. It's not like magic is being performed. Now you see there's only two hydrogens now. I'm going to put off this one. You see, because we broke now that Br plus, you see it uses both the electrons in the pi bond here to create that bond. So this carbon now actually becomes positive because it used to be sharing its it lost both electrons in here, you see. They're up here now, creating that bond. So what has to happen then is you don't forget that this is still hanging. That is carbonium ion, a very unusual one, Cr plus. So what has to happen now is that the Br minus now is still, or some Br minus still floating around, and it then is obviously attracted to the positive, and you end up then with a carbon, and a Br off that one, the Br that we attached first there, and then you also have the hydrogens coming off each of those. And that's essentially what happens. Now this is actually I've gone into this in a very bit of detail, you know, and there's actually an intermediate here. It turns out that this Br makes sort of a cyclic structure for just a split second between the carbon and the Br, but there's still a positive charge in here, so you still get the attachment of it, but I wouldn't worry too much about that, or indeed this overall reaction for now. I mean, that's one of the most complicated things in leaving cert that you're expected to be able to understand and reproduce, but I've introduced it now rather than me just saying that it is because it is. And the reaction with potassium and manganate, I wouldn't worry too much about this. Is oxidized, effectively potassium and manganese and oxidizing agent. Worry about that more when we study oxidation agents. It's convenient, we've talked about that already. It's a dehydration reaction of ethanol, and ethanol is the one. Alcohols are a family of an organic family as well, just like the ones we're studying at the moment, ethene or alkenes and alkanes. But ethanol is a member of the alcohol family. Physical properties, lower members of it. So you see a lot of patterns with this compared to what we did before. Lower members in terms of the alkanes. Lower members of the alkenes up to include butene are gases at room temperature. Remember, they're non-polar, they're not that attracted to each other. You need to slow them right down, i.e. cool them before the attractiveness that is due to, remember we talked about this in another video, temporary dipoles. So that's what they have to rely on. Because they're non-polar. They're not soluble in water for the same reason that alkanes are not soluble in water. They're non-polar and water is highly polar. It's not that the alkenes don't want to mix with water, it's that they can't because the water is holding together so strongly. But they will dissolve in things like cyclohexane, which is non-polar. So they will dissolve in other non-polar quite simply because then it's just non-polar mingling with non-polar. The boiling points of alkenes look something like this. And there's the boiling point increases with number of carbon atoms per molecule. And alkanes versus alkenes, again, you see, alkanes have a slightly... Now, why that is the case, you need to think about what's the fundamental difference between the two, and that answers the question. There's not a huge difference, but you see clearly, like, the general trend is exactly the same. But if you look at the alkenes, they're all a little bit lower. And that is because of the fact that the presence of the double bond, that area of high electron density, that is the double bond. The other really funny thing about them is alkenes are said to be planar. Now, what that means essentially, and we'll finish on this then, that's enough in one video. What that effectively means is, if I take the molecule again that I had there, if I was to take an example of a there is ethane. You see? Ethane, all the molecules, all the atoms are in different planes around this carbon. You see, they're all off in different directions. Whereas if you take a molecule of, it's easier to think of it when there's just one. If you take a molecule of, there's ethene. Now look down the end of that molecule. See, they're all in the same plane. So every atom that's bonded to this carbon, whether it's this one, or this one, the other carbon, are all in the same plane. So you can look down. And that's a thing you need to be able to do in chemistry, you know, be able to turn molecules like so in your imagination. But you don't necessarily, actually some universities allow you to take in these molly mods to help you study it. It's called stereochemistry. But look at it, if you look down that molecule, see, it's all flat. Now it doesn't matter if other, like if you had another molecule bonded on here and it went on then and it wasn't planar, if you like. But what you can be quite sure is every atom around this carbon is in the same plane. Now, just the next atom, not all the atoms, just the next atom bonded to this carbon. And likewise for this one. And that's why it's said to be, they're said to be planar. Whereas you see, look at, they're not planar carbons. You look down the end of that, everything's away every which way. They're not all in the same plane. And if you compare the two of them, you see, you can look down the end of that and see that they're all in the same plane, but these are away every which way, different planes. So in essence what I'm trying to say here is that carbons involved in double bonds are planar. And that means that every atom that's now directly attached to that carbon is in the same plane as the carbon. Be careful now. You could have a case where the molecule goes on. You can have both planar and non-planar carbons in a molecule. I mean, this is an example of one. I mean, that carbon, look at, if we look at this one here, every atom it's bonded to is in the same plane as it. That one, and that one. If you look down, you can see that. See, that one, and that one. Whereas then it's bond, that's a tetrahedral one. This one here is non-planar. Because look at, if you look down, look at, this one's away that way, that's away that way, that's away that way, and that's away that way. They're not in the same plane. So it's the carbons involved in a double bond that are said to be planar. And the ones not involved in double or triple bonds, indeed, are non-planar. And in this case, this one is tetrahedral, away 1, 2, 3, 4. And you remember that from the Whisper theory. So just think about that. Its carbons are considered to be planar or non-planar. So sometimes people get that mixed up. Now it's true the overall molecule could be non-planar, but that's an aside. And that brings us to the end today. So that geometry is quite important. The other thing I would say to you as well is, you see here with an alkane, you can twist an alkane. This is probably a bit much for leaving there, but anyway, it's no harm to know it, be aware of it just in case something like it is asked. See that molecule can twist as much as when you have an alkene. You can't twist it because of the double bond. It's locked. So that's another little thing you can know. Now that would be real top end chemistry, but I don't see the harm in telling you that. Okay.